Good evening, everyone. In our paper, we address the problem of matching shapes or regions across disparate images, by which I mean images with extreme variability in viewing conditions. Image matching using shapes or pixel level features is one of the oldest and well explored problems in the field of computer vision. And there is ample amount of literature in image matching using pixel based script like SIFT, surf, and geometric blur, and so on, to shape based descriptors like counters. But when it comes to disparate images where the variations are too high, let's say, for example, a day versus night, or historic images versus new images, or images with a high amount of occlusion, and so on, and especially images with high viewpoint variations and so on, it makes the traditional approaches infeasible. So in our paper, what we propose is we propose a novel multi-criteria optimization, where instead of matching pixel-level features or contours extracted from source image in the target image, we compute a joint image graph and match persistent regions extracted from it via geometric graph embedding. So how do we do that? First, let's consider graph G with V vertices. So each vertex is a patch or a region in the image. In our case, we use a key point extracted using geometric blur feature. So each vertex is a key point, and each vertex is connected to every other vertex using edges E, and each edge has a weight W. So what W represents is affinity. That means how close the vertices are in the feature space. So now this is for a single image framework. Now let's extend this to a joint image framework. So how do we do that? As I mentioned, the affinity matrix W, where W1, W2, and C are the submatrices that makes the affinity matrix W of the joint image graph. So W1 is the affinity matrix that I just explained, which has the distances between vertices of image 1 with vertices of image 1 itself. And similarly W2 for image 2. And C is the distances of vertices of image 1 and vertices of image 2. And by using this framework inspired by Mayank Bansal et al., we represent the affinity matrix W, and then we compute the eigenspectrum of the affinity matrix W and separate the eigenspectrum of source and target images. So the assumption is that if there is a common region across two images, then the eigenspectrum of source and target image should correspond. So by doing so, we do not have to compute the distance using the feature space, whereas we can compute the distance using the eigenspace. So our optimization is explained in the last equation, where the first term is just what I explained. I mean the distance is an eigenspectrum space, followed by a regularization term for which we use mean pixel intensity or Hawk features, just to make sure that the optimization is much robust. And in addition to the approach, we propose a data set of disparate image pairs with variations ranging from more occlusions and model versus sketch versus real images and so on. And each pair has one dominant object, that's assumption, and we have 40 such image pairs. And here's a link for the data set. We also provided the annotations for each images, ground truth annotations. And here are some of the results of the proposed model, where the green bounding box in each image represents the ground truth annotation. So ground truth is provided in a way that we find a common region across source and target images, whereas the red bounding box represents the estimated region correspondences. So if you see the first and second column, which are SIFT and geometric blur features, just raw SIFT and geometric blur features, you can actually see that they confuse the whole image as a corresponding region, and they cannot actually localize any region, any specific region as a match. Whereas if you see the column 3, we actually can find the most dominant shape in the particular image and then actually match them in the target image. And here are some of the quantitative results. The first two tables represents the results of comparison of our approach with respect to other feature-based approaches like SIFT, ORB, SURF, FAST, and GB, along with a shape-based approach from which our model is inspired, MSERFEM. And you can see that our approach performs significantly better than others, and there is a comparison with and without regularization as well. The last column represents our approach without regularization. So in that case, regularization to some extent affects the performance of the proposed approach. And we compare same experiment. We run the same experiment on an existing data set, which is proposed by Novus Navelli, which addresses the same problem of image variability. But the thing is, the existing dataset is not that challenging. As you can see, our proposed approach performs significantly better on the existing dataset than our proposed dataset. And table 3 and 4 provides a comparison of our approach, which uses geometric blur features with respect to other feature descriptors like SIFT and R. So we chose geometric blur features because geometric blur features have inherent ability to localize foreground and background. And so, I mean, as you can see, the geometric blur features perform better than others. And as I mentioned, I mean, like our approach is independent of the feature descriptor. You can actually use any feature descriptor you want. So that's pretty much it for the presentation. And if you have any questions, visit my poster.